Hey, this is Leach with Simpson Math, and today we're talking about the normal distribution. We will be using technology to answer normal distribution questions, which are in context and not just standard normal distributions, but distributions in context. Today we'll be looking at an example where we are dealing with the volume of Dr. Pepper in 12-ounce Dr. Pepper cans. Interesting note is that here in Temple, Texas, that there is the Temple Bottling Company, which bottles Dr. Pepper among numerous other sodas. So this is a question that hits home for some of us. So manufacturers of products have to make sure that they at least meet their advertised claim, including their claims of weight and volume. So suppose for a 12-ounce can of Dr. Pepper that the Temple Bottling Company actually has a goal of filling all cans to 12.07 ounces on average, with a standard deviation of 0.04. So again, they have to overfill just slightly, so that way most of the cans that they sell have at or over 12 ounces of Dr. Pepper. So let's make sure that we're clear about what our random variable and our distribution is. So X, it's the volume of Dr. Pepper in an advertised 12-ounce can of Dr. Pepper. And our distribution is going to be modeled by the normal model with a mean of 12.07 and standard deviation of 0.04. So the question that we're trying to answer is, what percent of cans are underfilled? Well, underfilled would meaning that I don't get 12 ounces, so that would be less than 12 ounces. So let's go to our picture first. And in our picture, we have our distribution with its mean of 12.07 and standard deviation of 0.04. In the last lecture, we would see how we would then tick mark off going down one standard deviation and another standard deviation, so that way we could use the 68, 95, 99.7 rule. But in this example, notice that this 12 ounces does not meet nicely on one of our integer z-score values. It's between it. So we're going to need to use technology to be able to figure out what this shaded area is. So to do that, I'm going to come over to Desmos, and I need to change distribution D. So it is no longer the standard normal distribution. So I'm going to delete the standard deviation of 1 and delete the mean of 0 and put in my new mean of 12.07, comma, my new standard deviation of 0.04. Now, I don't see it on my graph anymore, so I'm going to press the magnifying glass. There we go. And now it is zoomed in and centered up with my mean of 12.07 and standard deviation of 0.04. Just like last time with the z-scores, I'm going to check the find cumulative probability box, and I want to find area less than 12 ounces. So that's a minimum of negative infinity, because we're going to go forever and ever and ever to negative infinity, and then all the way up to 12 ounces. So I'm going to delete whatever's here and then type in 12.0 ounces. From Desmos, we get 0.040059, blah, 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 blah. Rounded to 4 decimal places, that's 0.0401. If I convert this to a percent, I end up with 4.01%. So the likelihood, assuming this distribution is what the Temple Bottling Company produces, then just over 4% of Dr. Pepper cans would be underfilled. Now, this is a pretty newer, more modern way of doing this, is doing it in a calculator like Desmos, or calculator that does these conversions for you. Just in case you're watching this video and you're wanting to see how to use z-scores to be able to answer this, because what if you just were able to find the z-score? So there's actually a different way that you could have worked this, but this is an optional approach. We could have stuck with the normal distribution being my standard normal distribution, a mean of 0, standard deviation of 1, and convert my 12.0 ounces using my mean and standard deviation in context into z-score. So I do 12 minus the mean divided by the standard deviation. So I get a numerator of a negative 0.07 divided by 0.04, and we get negative 1.75. Notice if you think about that or skip count around, that also, knowing this also helps you put the 12.0 in the correct location. So then the probability that x is less than 12 is the same probability that z is less than negative 1.75. So notice if I plug in from negative infinity to negative 1.75, I get the exact same thing. So there's two ways to work the same one. Like I said, what is in this light red is optional down here. That's obviously a little bit more math, a little bit more of the mathematical approach to do this. What Desmos does for you whenever you say what your mean and standard deviation are in context is it does all this math and those conversions automatically. All right, so just a follow-up question with this. If you were to buy 6 12-packs of Dr. Pepper, about how many cans would you expect to be underfilled? So, well, if I bought 6 12-packs of Dr. Pepper, just how many cans is that? Well, I would just do multiplication. 6 times 12, that's 72 total cans of Dr. Pepper. Yay me, lots of Dr. Pepper. And then what percentage of those are underfilled? Well, that's that 4.1%. So if about 4% of 72 is underfilled, how do I find that number? Well, I'll do 72 times 0.0401. Remember, when we do multiplication, we have to do it with the multiplication percents. We have to do it at the proportion level. And we end up with about 2.88272 cans. So about 2.89 cans we would expect to be underfilled. And in this case, it's okay for that to be a decimal approximation because this is what we expect to happen on average. All right, next, what percent of cans are over 12.18 ounces? So as always, let's start with our picture. So here we have our mean of 12.07, standard deviation 0.04, and way over here we have our 12.18. And it's almost even, you almost can't even see it, but there's a little bit of shading right above 12.18. I got this number because I knew that if I go up 0.04, we're at 12.11. If I go up another 0.04, we're at 12.15. If I go up another one at 3 standard deviations, this will be 12.19. So this is just a little bit less than that. By doing this picture, it helps me know my answer is going to be quite small. If I do this and my picture on Desmos ends up being a lot larger shading, or my number's a lot bigger, then that tells me that I've probably done something wrong. All right, so let's put this into the calculator. So it's my lower bound this time is 12.18. So I'm going to type in 12.18. It now underlines both blanks in red because they're saying, oh, this is not right. My smaller number is bigger than my bigger number, so we need to fix that. And I'm just going to fix that by, well, deleting my bigger number because I now want to go up to infinity. So notice I get 0.00297. So I end up with a pretty small number. If I convert this to a percent, we end up with 0.298%. So very, very, very tiny chance that I would get a Dr. Pepper that is that full. And again, optionally, just to see this work again, using z-scores, I could convert my 12.18 into a z-score by subtracting the mean divided by the standard deviation. And when I do, I get 2.75, which made sense when I skip counted by 0.04s, and I knew that 12.18 was just a little bit less than 3 standard deviations above the mean, and that's what we get. So from this, we know that the probability that I get a can that is bigger than 12.18 ounces is the same probability that z is bigger than 2.75. A z-score of 2.75, that's 2.75 standard deviations above the mean, and so that's 0.00298. Notice these numbers are the same. All right, let's move on to the next one. About what percent of cans are between 12.08 ounces and 12.17 ounces? So let's go to my picture first. So 12.08 is just about here, 12.17 right there. and I'm looking for this area in between. So I'm going to go to my calculator and do the same thing. 12.08 to 12.17. And we can see our shaded area in our picture that Desmos gives us. And we also can see that it's about 39.51%. So there's that from the notes. And so my answer is that it's 39.51%. And so notice, again, this is saying that x is between these two numbers, and that's what we can get with our picture. And if you wanted to do this with z-scores, you can just convert them into z-scores as well. If you do that conversion math, you can do that conversion math. I didn't show you this time, but do the conversion math and then type in the z would be 0.25, and the second z would be 2.5. So from 0.25 to 2.5 is that same area. All right, letter E. The highest 20% of cans are filled to what amount? So we're going to need to, again, go to our picture first. Let's do a quick sketch of our picture. Highest 20%. So somewhere is the top 20%. I need to draw my line right here because if I'm at 1 standard deviation and go up, that's 16%. Since this is 20%, I can scooch over just a little bit to the left. So notice this is just a bit to the left of 1 standard deviation up. So that's how I got my picture. Secondly, in order for me to put this into the calculator, I need to do a few things. One, I need to do the inverse stuff. And secondly, I need to figure out that the area less than my line of interest, less than the number of ounces, is 80%. Because remember, for the inverse process, you can only put in percentiles. So let me go to the calculator first. So I already have it equal to D. So I have D equals my distribution. I had that from the beginning. If you don't, remember to add that letter. Then onto the second line, I'm going to say D, and then dot, and then go to functions, and then inverse CDF. And then in the parentheses, I need to put my percentile, so my 0.8. So what this does for us is not only does it do the math to figure out z-scores, it then automatically then even converts it to units. So this number right here that is the 12.10, that 12.10, that is in ounces. So the powerful thing about doing this with Desmos is it automatically does this conversion for us. Oh, also, I don't need that shaded region, so I'm just going to uncheck the cumulative probability. There we go. So that 12.1 is our ounces. So it looks like this, again, just so that you can see it in our notes. And like I said, this must be a percentile. If you type in 0.2, let me show you what happens if you do 0.2. If you do 0.2, we get a number that at first glance makes sense. We get 12.037 or 12.036. But 12.03 is over here. And if it's the top 20%, that doesn't make sense. Top 20% has to be above 12.07. So always, whenever you, especially when you do this inverse stuff, this is why we do the picture. It sort of kind of helps you be self-checking to make sure that you don't have it on the wrong side of your mean. So use that picture to help you out. All right, so just to write my answer as a final statement, it is just x is 12.103 ounces. In with the probability statement, it would be like this. All right, let me show you the completely optional approach to find this value in context, but using z-scores. So first, let me go to the calculator. So this has my standard normal distribution, mean of 0, standard deviation of 1. I put in that same 0.8, but this number that's come out, this is a z-score, right? That's my z-score, number of standard deviation. So at 0.84, so if this was 1, doesn't it make sense, and this is 0, the mean 0, standard deviation 1, doesn't it make sense that that's about 0.84, just a little bit less than that 1? So now I can take that 0.84 and convert it to context. So my formula is z equals my value minus the mean divided by the standard deviation. So z is my unknown value minus the mean divided by the standard deviation. Then we go through the process to solve. So multiply both sides by 0.04. 0.04 reduces from the right-hand side, and we're left with on the left-hand side 0.033664. Then add my 12.07 to the other side. Those cancel to 0, and I'm left with my number in context is 12.103 ounces, which is what the calculator gave me just a second ago. All right, lastly, let's find the IQR for the amount of Dr. Pepper in the cans manufactured at this plant. So remember, IQR is the middle 50%. In our last video, we talked about doing the middle percent dance, about finding a middle percent. This middle percent is special because it is the IQR. So that means the endpoints that we're going to be finding are not just any old regular endpoints. They are Q1 and Q3, the first and third quartiles. So let's draw our picture. So this is the middle 50%. We can do the middle percent dance. I know that everything adds up to 100%. In the middle, this is 50%. So 100 minus 50 is, well, 50. So collective in the wings is 50%. Take that 50%, divide it by 2, and we end up with 25%. So only one of these wings is 25%, which should make perfect sense, because 25 plus 50 plus 25 is 100. Also, like I said, if this is IQR, this 25th percentile must then be that this is, like I said a second ago, that's Q1, and this is Q3. So this is the 25th percentile, and then this would be the 25th percentile, which is Q1, and this would be the 75th percentile, or Q3. So in my calculator, I'm going to put in 0.25 for this first quartile, or 25th percentile, and then I'm going to go ahead and just quickly type in D point inverse CDF of 0.75, and then I get my Q3, or my 75th percentile. Because remember, you have to type in area to the left for both of those. So from here, that way, that's 25%. Here, this way, that is 75%, 25 plus 50. So here's my notes already done. Notice I use this 25%, and then to get the 75%, it was the 25 plus 50. So as a final answer, my lower bound, or Q1, happened to be 12.043, and my Q3 was 12.097 ounces. Additionally, we need to find the IQR. The directions say, find the IQR. And actually, just a second ago, I just realized I forgot to actually answer the question. So my final answer is actually not my lower bound and my upper bound being listed out, but my answer is actually the fact that the IQR is Q3 minus Q1, which is my 12.097 minus 12.043, and it equals 0.0537. So the IQR of this distribution is about 0.05 ounces. Right? And like we did last time, we can also do all this using z-scores as well. So I get my z-scores from the calculator, negative 0.67 and positive 0.67, and then use those to find my decimal approximations. So here, I do the same thing, the negative 0.67, x minus the mean divided by the standard deviation, go through the same solving, and we get 12.043, which is what we got a second ago. For my upper bound, or Q3, now is a positive 0.67, same math, multiply and add, and we get 12.097. And then we can do the subtraction for the IQR again, and we end up with 0.0537. All right, there you have it. That's how we can use technology, specifically Desmos, to find answers to these normal distribution questions, both where you're given x's and have to find percents, and given percents and have to find the x values, the values in context. I hope this helps, and I'll see you next time.